How can a train turn when its two wheels are literally connected by the same axle? Think about it for a second. Imagine two wheels connected by a solid metal rod. If the wheels are locked together, they have to spin at exactly the same speed. But when a train enters a curve, the outside wheel has to travel a longer distance than the inside wheel. So how can both wheels possibly make the turn? It sounds like a problem that should make a train derail, but trains have been solving this problem for more than a century, and the secret is hiding in the shape of the wheels. Before we reveal the secret, hit like and subscribe for more fascinating facts. Now, let's get back to the mystery. At first glance, train wheels look almost flat, but they aren't. Their surfaces are carefully designed with a slight cone-like shape, and that tiny difference changes everything. To understand why, imagine riding a bicycle around a curve. When you turn, your outer wheel travels farther than your inner wheel. That's easy because bicycle wheels can rotate independently. The outside wheel can spin slightly faster than the inside wheel, but a traditional train wheel set doesn't work that way. The two wheels are fixed to the same axle. If one wheel rotates, the other rotates at exactly the same rate. So here's the strange part. The train doesn't make the wheels spin at different speeds. Instead, it changes the effective size of the wheels. And this is where things get clever. Imagine that the wheel isn't one uniform circle. Instead, imagine its rolling surface has different diameters across its width. If the wheel set moves slightly toward one side of the track, one wheel ends up riding on a slightly larger part of the wheel, while the other rides on a slightly smaller part. Now both wheels are still rotating at exactly the same speed, but they are traveling different distances with every rotation. Why? Because a larger circle covers more distance in one revolution than a smaller circle. That's the trick. The train doesn't need its wheels to rotate at different speeds. It makes the wheels behave as if they have different sizes. And suddenly the impossible problem starts making sense. But there's an even more surprising part. The train doesn't have to actively tell the wheels to move sideways. There isn't a tiny steering mechanism underneath the train deciding, okay, we're turning left now. The geometry of the wheels and rails does much of the work automatically. As the train enters a curve, the wheel set naturally shifts slightly across the track. That shift changes which part of each wheel is touching the rail. The outer wheel rolls on a slightly larger effective radius. The inner wheel rolls on a slightly smaller effective radius. And because the wheels are connected, they still rotate together. The difference in their effective diameters allows them to cover the different distances required by the curve. Think about it like this. Take two circles and connect them with a rigid rod. Now imagine one circle is slightly larger than the other. If they rotate together, the larger circle will travel farther with every revolution. That simple geometric idea is at the heart of how train wheels negotiate curves. But there's one thing that makes this even more fascinating. The wheels aren't shaped this way just to help trains turn. The same design also helps keep the train centered on straight track. When the wheel set moves slightly to one side, the effective rolling radius changes. That creates a natural tendency for the wheel set to move back toward the center. So the wheel geometry is doing two jobs at once. It helps the train follow curves, and it helps guide the wheels along the track. But what about the raised edge you can see on the inside of many train wheels? That's called a flange. You might think the flange is what keeps the train on the track and makes it turn. And it certainly plays an important safety role, but it isn't the main reason a train can smoothly negotiate ordinary curves. The wheel tread geometry does much of the subtle steering. The flange is more like a backup guide. It becomes especially important when the train encounters conditions where the wheel set could move too far sideways. And now think about how remarkable this really is. A train can weigh thousands of tons. It can carry hundreds of passengers. It can move at extremely high speeds. And yet, one of the key mechanisms allowing all of that weight to follow a curve depends on a tiny difference in the shape of a steel wheel. No steering wheel. No engine controlling each wheel separately. No computer telling every wheel how fast to spin. Just geometry. But there's still a problem. If the outside wheel needs to travel farther, why doesn't the wheel set simply slide sideways forever? Simply slide sideways forever? Because the geometry works in the opposite direction too. As the wheel set shifts laterally, the difference in effective rolling radius creates forces that tend to guide it back. So the wheel set constantly interacts with the rails. A tiny sideways movement changes the rolling geometry. That changes the forces acting on the wheels, and those forces help guide the wheel set. It's almost like the train is continuously correcting itself, and that leads to an important idea about engineering. Sometimes the smartest machine isn't the one with the most complicated computer. It's the one where the physical shape of the machine naturally produces the behavior you want. A train wheel doesn't need to know that it's entering a curve. It doesn't need to calculate the distance between the inside and outside rails. The shape of the wheel and the position of the rails create the solution automatically. But there's another detail you probably never notice. Train tracks themselves are not perfectly flat. On curves, engineers can sometimes raise one rail slightly higher than the other. This is called superelevation, or cant. Why? Because a train moving through a curve experiences forces that push it outward. Raising the outer rail helps balance those forces and allows the train to move through the curve more smoothly. So when a train takes a curve, you're not looking at just one clever invention. You're seeing several pieces of engineering working together. The wheel shape, the axle, the rails, the flange, and sometimes the angle of the track itself. All of them are quietly solving a problem that seems impossible when you first think about it. And here's the part I find most fascinating. If you look at a train from the outside, it seems incredibly simple. Two steel rails, steel wheels, a massive machine rolling forward. But underneath that simple appearance is a carefully designed system where geometry, friction, forces, and motion are constantly interacting. The train isn't fighting physics, it's using physics. That's the real secret. The wheels don't need to be independent. They don't need to spin at different speeds. They simply need to be shaped in a way that lets the same rotation produce slightly different distances. And that tiny idea allows thousands of tons of steel to smoothly follow a curve. So the next time you see a train disappear around a bend, remember what is actually happening underneath it. Two wheels are still locked together. They're still rotating at the same speed, but because of their carefully engineered shape, one effectively rolls farther than the other. And somehow, a problem that seems impossible becomes completely natural. Maybe that's what makes engineering so fascinating. The most impressive solutions aren't always the things we can see. Sometimes, they're hidden in something as ordinary as the shape of a wheel. And once you understand the trick, you'll never look at a train track the same way again.